Okay, so in this video, we are going to talk about how we can simplify big O expressions. We've talked briefly about this while going over some examples in the previous videos, but in this video, let's just dedicate ourselves to simplifying big O expressions. And right off the bat, let's start with an example. So here we have these operations. We have the first three assignment operations, one for the nums array, one for the n to find the length of the array, and the other for the sum. We also, of course, have our loop, and for that loop to even work, without us even attempting to see what's going on inside, we can count 3 n operations from this loop declaration alone. Because to create a loop, that means that we have n assignments for the I variable, n additions because we increment I with each pass, and of course n comparisons because we would need to verify that whatever the case that checks whether we should continue the loop is still on. So that's 3 n's right there. Inside our loop, we also have 2 n's. An addition because this addition would happen n times since it's in a loop, and similarly n assignments. So the number of operations that we have here is actually 5n plus 3. So the complexity should be big O of 5n plus 3, right? Well, no. That's because the first rule of simplification is that we ignore constants. So if we have a complexity that follows this formula, an plus b, where a and b are constants, we would ignore a and b. We would just say that this complexity is big O of n. And of course, following that logic, the 5n plus 3 we saw earlier is actually equivalent to big O of n. And that ignore constants rule is the reason that we say that constant complexities are equivalent to big O of 1. It doesn't matter if your constant is 5, 500, 5000, it's still a constant. So we would just represent it by 1 and say that constant complexities are big O of 1. And that's also the reason we don't say, for example, 5n squared, 5 is a constant. So we just ignore it. It's just big O of n squared over here. Okay, so what other rules do we have? Well, we also ignore the smaller terms. Now, what do I mean by this? Well, consider this formula right here. How would we actually represent this formula in terms of big O? You might think that the answer would be n squared plus n, just remove the constants. But no, the complexity here is not big O of n squared plus n. It's actually just n squared. The reason for this is fairly simple. N is a smaller term than n squared, and like constants, we ignore smaller terms. That's because the impact that n squared will have on the function, on the runtime, would be so great that adding n to it doesn't really make a difference. Now, a couple of notes before we continue with more examples. Arithmetic operations is, like you saw previously, considered constant. A single arithmetic operation is a constant operation. Also, direct array element access is too considered a constant. Now, let's see another example. What is the complexity for this function over here? Pause the video, give it a second of thought, and then continue. Okay, so the complexity is actually big O of n squared. But how? Well, that's because the complexity in this case is simply equal to n, which is the outer loop, times 2n, which are the two separate loops that we have nested in our main loop. Basically, we have a loop that contains two nested loops. Each nested loop will run n times. That means that both of them will run 2n times. Now, these two n operations will actually happen n times itself, which means that our complexity is actually equal to big O of 2 multiplied by n squared. And since we agreed that we should ignore constants, that means that the complexity is big O of n squared. In the next video, we're going to talk about space complexity analysis. See you then.